Hello, here I'm Andrea Angella, and in this video we're going to solve the paper 33, October-November 2015, Advanced Theory, Computer Science A2 level. So let's go and do it. Okay. The first question is about floating point number representations. We have 8 bits for the mantissa and 8 bits for the exponent. So the whole idea is of a floating point representation is basically to represent the number as a mantissa and an exponent. We have the first question. We have a mantissa and an exponent, and we want to calculate what's the denary value of this number. So the way it works is it's basically you need to consider that the exponent is an exponent of 2. So we are gonna basically the number is gonna be something like this: m by 2 to the exponent. Okay. So m is the mantissa and e is the exponent. Okay, so we need to see what's the value of the mantissa in denary, what's the value of the exponent in denary, and then replace these two values in this expression, and then calculate the value. So, what's the value of the mantissa? Okay, the first digit is basically the integer parts of it, and then the bits afterward are actually the decimal part of it. So basically, you get this number. So the leading zero doesn't matter. So the mantissa is basically 0.0101. Okay, and then this is going to be multiplied by 2 elevated to, and the exponent is basically 3 in decimal. Okay, so if you multiply a binary number by 8, it's basically like moving the comma of 3 positions to the right. So it's basically similar to multiplying by 1,000 in the decimal system. So here we're going to move the comma 3 positions to the right, and the number will become 10.1 in binary. And this is in binary, and in let me put an equal sign at the end. And if you convert 10.1 in actual denary, what do we get? We get 10 is 10 is basically 2 in denary, plus 0.1 is actually 1/2. Okay, so the result is 2.5. So this is basically how you can convert a floating point number to denary. Okay, you calculate what the value of the exponent is. You move the comma to the right or to the left based on the value of the exponent, and then you convert the result in denary. You take the integer part of it and you add the decimal part of it. You need to remember that if the decimal part of it is basically 1/2, 1/4, 1/8, and so on. If you move right, you basically go 1/2n. So let's say if I have something like 0.01, this 1 is basically equals 1/4. If you get 0.001, this is going to be 1/8. Okay. So for the integer part, you get from 2 to 4 to 8 to 16. While if you go on the right side, in the decimal part, each bit is 1/2, 1/4, 1/8, and so on. It's pretty much similar to what you have in the denary system, but obviously we are working in binary here. I see this is actually the answer. Then explain why the floating point number in part I is not normalized. So it's very common to in the computer system that to normalize numbers to make sure that the precision and the accuracy of the number is at its best. And the normalization requires that the mantissa start always with 0, 1 for positive numbers. So why is not normalized? It is not normalized because the mantissa does not start with 0, 1. Right? If it is positive, you need to start with 0, 1. Then we've been asked to normalize it. So in order to normalize it, we need to make sure that this number mantissa actually start with 0, 1. So we need to have a 0 here and a 1 here. How can we do that? So you need to think about how much I need to actually shift the command. Oh, I should be able to do this. Yeah. Something not working with the tool. There we go. So in order to have a 0, 1, the first two bits here, what we need to do, you can see that 0, 1 is it's a second and third bits from left to right. So you can see that we can actually shift the mantissa one position to the left in order to have the mantissa starting with 0, 1. So this means that we need to multiply the mantissa by 2. Okay? So if we multiply the mantissa by 2, so we basically shift left the mantissa, what we have is going to be 1, 0, 1, 0, 1, 0, 0, 0, 0. Okay, but because we multiply the mantissa by 2, in order to make sure that the number is actually the same, we need to divide by 2 somehow. And how we can divide by 2 is simply reducing 1 from the exponent. So the exponent was 3, so we're gonna have 2 as the exponent, because now we are gonna multiply only by 4 instead of 8, because we already multiplied the mantissa by 2. Okay, so this means that we are gonna preserve the actual value of the floating point number. And at the same time, we actually achieve normalization, because this is actually, oops, I don't want the filling point. So if I, sorry, take that and remove the background. I don't want to have any fillings. So if basically this one doesn't work, sorry. The first two basically are what makes this mantissa normalized. This floating point number normalized. Okay. Next. Oops. Next. The next question is, write the largest positive number that can be written as a normalized floating point number in this format. Okay. So what is the biggest mantissa that we can have? So if you want to have the biggest possible number using this mantissa and exponent approach, what you want to have the highest possible mantissa and the highest possible exponent, so that the result will be the highest possible. So what's the highest possible mantissa? So we know that we want a normalized, pay attention, we want a normalized floating point. So we already know that we must have 0, 1 at the beginning. Okay, so if we have 0, 1 at the beginning, what's the highest mantissa that we can have? Basically, it's going to be all 1. If we have the mantissa to be all 1, we're going to basically have 1/2 plus 1 out of 2, 1/2 plus 1/4 plus 1/8 plus blah 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 blah. So basically, it's worth to have a number, a 1 in each single position, so that basically we maximize, we make the number as high as possible. Oh, actually, I didn't. Okay. So if you do this, we are sure that we are basically having the highest mantissa. For the exponent, pretty much similar. Because this is the complement by the two complement of a number, the highest possible positive number using 8 bits in two complement is actually even 0 and all 1s. Because if we put 1 at the beginning, then the numbers become negative. Okay, but we don't want negative number. We want to have the highest possible exponent so that we get the highest possible result. Okay, so basically, if you do something like that, all 0 followed by 1s, both for mantissa and exponent, you get the highest number. Then we want to write the smallest positive number that can be written as a normalized floating point number. The smallest positive number. Okay, what we want to have the smallest possible mantissa. Okay, positive. So we know that we want 0 here, and we know that we want 1 here. And if we do not provide any other ones, basically this is the smallest possible positive number that we can have in a normalized way. That is actually 1 over 2. And the exponent, if you think about the exponent, if you have the expression m by 2 exponents, if the exponent is negative, you are going to get a very small number. So what we really want here, we want to have e to be the highest possible negative number in absolute terms, right? If I have 2 elevated to minus 2, okay, it's going to be, if you have 2 elevated to minus 4, it's going to be even smaller, the resulting number. So the highest is the absolute value of a negative exponent, the better, the smallest is going to be the number. So what we want having 1 here, because we want a negative exponent. And what is the highest negative number? It's basically using all 0. Oops. I don't know what's going on here. 0 here, 0 here, 0 here, 0 here, 0 here, 0 here, and 0 here. Okay, so this is the highest possible, the lowest possible exponent, okay, or the exponent with the highest absolute value as a negative number. Okay, and this is actually the smallest number you can form. Okay, so when you have a question like that, if you want to create the largest positive number, you need to have 0 followed by all ones for mantissa and 0 followed by all ones for the exponent. If you want to want the smallest positive number, you want to have 0, 1 followed by all 0 for the mantissa, and you want to have 1 followed by all 0 for the exponent. If a positive number is added to the number in part bi, explain what will happen. Okay, when you add 1 to a floating point number that is already the highest possible positive number, are not able to represent this number anymore, and then an overflow will occur. It usually makes the number, becomes negative. So let's put this in Word. An overflow occurs. An overflow occurs because the number is too big to be represented. Okay. Then we have a student who writes some code, and the student is surprised to see the program outputs a sequence like 0.0, 0.1, 0.2, 0.2, 9999 instead of 0.3, for example. And why this is happening? The problem with the floating point number is that not all possible numbers can be represented exactly. So 0.1 in this case, that is added every time to x, can't be exactly representing using a floating point number. And so this means that if you add it repeatedly in a loop, at some point the error that is accumulated during the loop will be visible, will be actually shown, and then the result will not be the exact number that you expect. Okay, so the more you add, the more you lose precision, in terms of the accuracy, in terms of the number. So basically what happened is that the value 0.1 cannot be precisely represented in binary. Okay, the loop constantly adds an imprecise number. After some iterations, the error becomes significant and visible. Basically, what happened is all because the 0.1 cannot be represented completely using binary in a way that is exact. Okay, so the next question is about a compiler. So we have a symbol table. So the idea of a symbol table that for every keyword of the language, for every symbol, you have a token number, and then you have entries in this. So this is the all the keywords tokens are in this range. So each keyword contains has a particular token, and we want to have entries in the symbol table are allocated tokens. These values start from 60, that is hexadecimal. So we have a symbol code, and we want to complete the symbol table. Only the symbols, right? So symbols are basically variable and constant, like counter, 1.5, numerical value, the counter, numerical value. So the symbol tables only contain the variable and constant, for example, in this case. So we already have counter and 1.5, that as basically is the token value 60 and the token's value 61, that is of type variable and constant. Okay, so if you look at the program, so basically the symbol table contains the list of all the symbols in order of appearance in the program code. The first two symbols that you find are counter and 1.5, and the next symbol is number 1. So num1 is the next symbol. And this num1, we can see, is going to be 62. So each symbol basically contains a value that is the order of appearance, if you think about that. So 63. So the first symbol is 60, then 61, 62, 63, and these are all the tokens basically of the language that are already kind of pre-populated because they are specific about the language. But the symbol is actually stuff that the programmer introduces as part of the code. And num1 is a variable, we know. And also we get, after input num1, we have if counter that we basically eat again, but we already have it, so we don't need to worry about that, equals num1. So num1 already ate it, then we get num1, and then 5.0. So 5.0 is the next symbol, and we know this is a constant. So basically, at the end of the processing, the compiler will have a full list of tokens that actually we've been asked here. We have basically the keyword table, and we want to get the output of the lexical analysis. What we get at the end of it is a series of numbers that represent the tokens and the symbols present in the program in order. So let's say at the beginning where we have 60 and 01. So counter is 60. We know that is the value of the token. Then we have the assignment operator. The assignment operator is actually 01 in code. So every single token of the program code is represented by a number. So the lexical analysis basically will produce a list of all of these numbers that basically contains the program code written in a way that is, precisely identify each single token and symbol. So in order to fill this this output, what we need to do is to actually look at the program in order and add the right value. So after 01, that is the assignment operator, is 1.5. 1.5 is the constant, and we know that the value is 61. So 61 is the next things to do. After assigning 1.5, we have input. We know the input from this table is 51. So then 51 is what we need to add here. After the input, we have num1. Num1 is 62. Then after num1, we have if, and if we know that the token value of if is 4a. And then we add 4a, and so on. So this is actually the way to do it. If you follow this, then after the if, what we have? After if, we have equals, and equals is 03. After the equals, we have num1 again, that is 62. Okay. Then what we have? Then we have then, and then is 4b. And after then, we have num1 again, that is 62. Then we have the assignment operator, that is 01. 62, 01. Now we know we have 62 again, because we are trying to add a number there. Then we have plus. Plus is 02. And then we have the number 5.0, the constant, and the 5.0 is value 63. I think I missed something. So let's have a look if I got everything. So 4A03. I missed something. After 4A is actually if. I miss counter. Counter is 60. I put 03 afterwards, but there is actually 60 here. So this is basically going to be moved. Sorry for this. Let's see if I can easily move this stuff. This is going to be here. It's going to be here. This is going to be here. This is going to be here. So it's always worth. It's very easy to make mistakes, especially if you scroll in these things. But it's always worth double checking every time to make sure that. The reason why I spotted this is because I've seen that basically I was here 63. That is the 5.0 constant, and I only had one token at the end of the program, and I still had 2 spaces left. So there was something I was missing. So 63 now is 5.0. I know there is only one token left. That's endif, and endif is 4c. So it's okay to make mistakes as far as you actually fix it, and after you double check. So make sure you do it properly. Make sure that you actually fill it right. It's just very mechanical the way to do it, but be careful. So the next step is we have the line of code A equals B plus C plus D. And we have, after the syntax analysis stage, the compiler generates some object code, and we have some code in the assembly language. Name the final stage of the compilation process that follows this code generation. After the code is being generated in a compiler, the next step is optimizing the code. Okay, so code optimization. Code optimization is actually what happens. What means is that the assembly language generated might not be optimal, so there might be things that are not required, can be removed. And for example, here we need to write the code after the optimization. So it's quite easy to see here what happens. So we load the value of the C, B, then we add C, so then the accumulator basically will be already B plus C, and then we store the value of the accumulator in 567, then we load 567 again. That feels a bit unnecessary because the value of the accumulator is stored and then reloaded immediately. So these 2 instructions are doing nothing, basically. Then we add D, and then we store the result of the accumulator in 233. So this means that we can actually remove these 2 lines of code, and the result code will be just load 234. That's the first instruction. Then there would be add 235. So this basically calculates A plus B. And then we can just immediately add 236 that are basically at C. And now in the accumulator we have B plus C plus D that we can store in 233 that store the result in A. Okay. 2 benefits. So state 2 benefits of the compilation process performed in this final stage. So the benefit is quite obvious. The code is faster because if the processor needs to run less instructions, obviously the code will execute faster. So the code executes faster. And obviously the other benefit is that the program code in terms of size is smaller, right? So less memory is required in order to actually load the program. So this is another main benefit. The code size is smaller. In memory, basically, is smaller. Okay? So less instructions, basically. Now we have an email. It is sent from one email server to another using packet switching. Stage 2 items that are contained in an email packet apart from the data. Okay, when you want to use packet switching, you're basically using the Internet Protocol's address, and each packet needs to have the source address and the destination address as an IP address, right? So these are actually 2 items that are always contained in packets to send emails or any other sort of information. Send this IP address and receivers. Oops. Receivers. Okay, now we need to explain the role of routers in sending an email from one email server to another. Okay, so the routers are basically devices on a network that helps to forward messages in the proper direction in order to reach a destination. And the routers can forward the message to other routers and so on and so on and so on until the destination is reached. And the packets could actually go into follow different paths based on different times, based on the status of the network, based on the usages and so on. So, but obviously the email is actually some text, some binary information that need to be split first into packets, and then all the packets actually are sent to the destination using routers, and then the packets are combined at the destination and to rebuild the original email. Okay, so that's kind of what happens. And the routers are actually extremely important in order to forward the message through the internet. So the email is split into packets. Routers basically use the packets destination address to forward them throughout the internet. And the packets are assembled at this destination to reveal the original email. Okay? Sending an email message is an appropriate use of packet switching. Explain why this is the case. Okay, so the reason is that packet switching doesn't create a dedicated circuit between the source and the destination. So there is no dedicated channel for that particular communication, and it's actually not needed for an email, because the main value of a dedicated circuit is actually to have a very high quality of service, very a dedicated channel, high bandwidth, no error loss, and stuff like that. With and we want to have the information to arrive in order based on how it's sent, like for example video conferencing or stuff like that. In the email, all of these requirements are not necessary and not necessarily relevant, because in order to be able to read the email, you're not going to need all the information. So all the information needs to be assembled together. It doesn't really matter the order of of how the packets arrived. Is what really matters is that at the end we can actually reassemble all the email. So basically we can say there is no need for a continuous series, because the email is only read when all the information is received and the order of packets is not relevant. Okay. So the next question is, packet switching is not always an appropriate solution. Of course, an alternative solution is actually circuit switching. That consists basically creating a dedicated channel. So I think is the question now asking, name an application for which the method identified in part D, that is the actual circuit switching, is an appropriate solution. Circuit switching consists of creating a dedicated channel with high quality communication. So if I want to do a real-time video, for example, real-time video is definitely an application that requires a very high bandwidth, requires a very dedicated channel with as less error rate as possible. And also the packets and the information need to arrive in order, so that you don't see the video in different in a different order or stuff like that. So circuit switching is extremely important for this kind of thing. So the main justification is basically the quality of service is guaranteed. I should be able to spell it. Yeah. So the quality of service is guaranteed because a dedicated channel of, let's say, circuits is created to handle the communication. How about that? So very dedicated circuits. The circuits provide a high bandwidth channel with no loss. Okay. Next question is about, okay, we need to actually connect each description to the appropriate type of processors. Okay, different type of processor, RISC and CISC. The RISC means reduced instruction set, and CISC means complex instruction set. The idea is that the RISC type of processor uses a lot of general purpose registers. So we're going to connect these two. And the idea is that there is a very simple set of instructions there is no complex addressing or complex instruction logic. The instructions are extremely simple. That's why there is a need of using a lot of more registers to do that. And while the CISC instead is actually having a lot of more address modes available. So, and different ways of addressing instructions. So these are actually the main how the description fit the type of processor. CISC usually a very little number of registers, but the instruction set is very complex. While the RISC use a lot of registers, but the instruction set is very simple. That's in the RISC processor, 3 instructions are processed using pipelining. And pipelining is definitely a technique that is very often used with RISC processors that allows to run different stages of different instructions at the same time, so that the throughput of instructions run is definitely higher. So, and an instruction can be, there are different stages for each instruction. In this case, there are 5 stages: fetch, decode, execute, access the operand memory, write the result to the register. And we can do all of these 5 stages in parallel at the same time. It's quite impressive. So what you need to do is you need to complete the table to show the time interval in which each stage of each instruction is basically carried out. So we have A followed by B and followed by C, 3 instructions. Okay, so we can do the first fetch of each of these instruction one after the other. In order to be able to do the code of A, we need to wait one time interval, because we haven't fetched the computer haven't fetched the instruction yet. So in order to decode A, we need to wait one. In order to execute A, we need to wait another interval slot. In order to access the operand, we need to wait another slot. To write the result, we need to wait another slot. Okay, and then basically B follow the similar pattern: B, 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 like that, and C, 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 like that. That means that after 7 time intervals, we are done. All the 3 instructions are completely executed. All the 5 stages of each instruction has been executed. While if we had to do this using a CISC processor without pipelining, basically we had to do all of the phases in sequence. So we should have done ABC 5 times. That would be 15 time intervals. And so, in fact, we need to say how many clock cycles we actually saved. So without pipelining, the number of cycles is basically 15. So 3 by 5 equals 15. 3 by 5. Okay. With pipelining is with pipelining is 7, we actually seen. So the saved clock cycles are 15 minus 7, that is 8. So we actually save 8 cycles. That means that we actually we have twice the performance in half of the time. We are able to do all of the 3 instructions. That's quite impressive. That's why most of the modern processors are using the RISC processors. Okay, now we have a Boolean function that corresponds to a truth table, and we need to write the actual Boolean function. Okay, so we have a table and we want to write a function. Okay, how to do this? It's fairly easy. We need to see where is the output at 1. There are 3 places: this line, and this line. So, and then for each of these places, we need to actually represent A, B, C. So, for example, the first one is already given, is actually representing not A, B, C. So it's a not if it's 0, and it's actually the letter if it's 1. So basically we have not A here, B and C. This basically represents 0, 1, 1, if you think about that. So it's actually the first line. Then we have the This line here that we need to add is A, B, and not C. So A dot B, B dot not C. I'm gonna do it now with an arrow like that, not C. Okay, plus the last row, that is 1, 1, 1. So that A dot B dot C. And that's how to write the Boolean function to correspond to the truth table. Look at all the places where the output is to 1, and then represent the input using each input as separating each input as plus, right? Then we need to actually fill the Karnaugh map. The Karnaugh map is a technique that is used in order to be able to optimize Boolean expressions. So you can fill the Karnaugh map looking at the location where the X output is 1, and then you put a 1 in the corresponding location. For example, not A, B, C. So you can see that the first line contains A and B, combination of A and B. So 0, 0, 0, 1, 1, 1, and 1, 0. There are 4 possible states for A, B, and each row contains only C, 0 and 1. Okay, so in order to do not A, B, C, we need to go 0, that is not A, B, that is 1, and then C, that is 1. So 0, 1, 1, and here we put a 1. Okay, and we do the same for the other two ones. So we have 1, 1, 0, so 1, 1, 0, it's this one. And then we have 1, 1, 1, so 1, 1, 1, and this one. Okay, all the rest is 0. So at the end of the day, you need to have the same number of ones in the table, like you have in the original truth table. So we have 3 ones here, and we have 3 ones here. Perfect, that's okay. Good, now we need to use the Karnaugh maps technique in order to actually optimize. So the techniques consist of finding the optimal sum of products, and we need to find groups. In order to find groups, we need to actually kind of aggregate. So I think, yeah, okay, let me pick color that is not red, let's say black. So we need to group ones where in as power of 2. At the moment, we don't have anything that like 4 ones together. So the only groups we can do is this one and this one. So you need to do the trying to cover all ones using the highest possible the groups with the highest number of power of 2 elements. Like we need to see if there are groups of 8. No way of doing groups of 8s. There's no way to do groups of 4s. Well, we can do 2 groups of 2. And the minimum number of groups we can do to fill the table is are these 2. And these 2 actually represent the the 2 the 2 elements that need to be summed in order to get the simplified expression. Okay, so what is the result? So you need to consider only the elements that do not change. If you consider this vertical group, C always changes, 0 and 1, so this should not be included. And then A and B will stay fixed, so that should be included. So A and B is basically the representation of the first group, while the second group, the horizontal one, you see that A always changes from 0 to 1, B is stable, and C is stable. So this is going to be B, DOS, and C. Okay, that's how you actually translate. It's actually a very nice technique for optimizing. Now we have a similar question, but asking to optimize a bigger function with 4 input variables, but the approach is fairly similar. So what to do? Again, for each combination of AB and each combination of CD, you need to actually fill this table. Let's put 0, 0, 0, 1, 1, 1, 1, 0. Here CD could be 0, 0, 0, 1, 1, 1, and 1, 0. It's very important that you put the numbers in a way that only one element, one bit change every time. So from 0 to 0, 1, only B change. From 0, 1 to 1, 1, only A change. From 1, 1 to 1, 0, only B change. So, okay, it's very important. Otherwise, the Karnaugh maps doesn't work if you mess up. Always use this order: 0, 0, 0, 1, 1, 1, 1, 0. Okay, so now same approach. How many elements at one do we have? 1, 2, 3, 4, 5. 5 elements. We expect to have 5 ones inside this table. So the first one is at location 0, 1, 0, 0. So 0, 1, 0, 0 here. The second one is at location 0110. 0110, that's here. The third one, this one, is at location 1100. 1100 here. The fourth one is at location 1110. So 1110 here. And the last one is 1111. 1111 here. Okay, we filled up. All the rest is zeros. Okay, good. Now we need to do the same approach, groupings. Okay, what is the biggest groups we can do? So this here can be a bit hard to do with this tool. Let's try to use the pencil to do it. Okay. Okay, what is the group with the highest number of elements you can have? You can have a group of 16, no. You can have a group of 8, yeah, no. You can have a group of 4s, yes. The important thing is that when you consider groups, you need to consider elements that are adjacent. So for example, this element here is adjacent to this. So you can do a group that go across the border. So like I can do a group like that. Wow, like that. Oops, sorry, like that. But these 4 ones here form a group. Okay, and then but there's one number left. In order to cover this number with the highest possible group with the highest possible elements, I can actually cover this using a group of 2. Okay, bear in mind, if you actually select only that, you still cover the table. You still will get an expression, but it won't be optimal. You need to make sure that you select the highest group, the group with the highest number of elements, so that you can make sure that the corresponding expression is actually the most optimal. So let's now convert this into a Boolean function. The first group of 4 bits is, let's have a look. Let's see what changed. A changed from 0 to 1. B is stable. C changed from 0 to 1, and D is stable to 0. So the result, the value is going to be B and not D. This is actually the value of the first part, and then you need to add this to this group here that contains A, B that's stable, C also stable. So A dot B dot C. Okay. Excellent. Then let's move on. We have a number of processes that are being executed in a computer. Explain the difference between a program and a process. Okay, that's fairly easy. Excuse me. A program is basically the code, the static code inside a computer, while when you run this program, then a process is basically created. So the process is the executing code. The code is actually currently executing. So I would say a program is the code, while the process is executing code. Okay. Then for process can be one of the 3 states: running, ready, or blocked. So when you are inside an operating system, yeah, a process can be different stages. Running means that the CPU is actually running this particular program. Ready means that the program is not currently running, but can be, is ready to be running. And blocked means that the program cannot execute at the moment because it's waiting for something else happening, like usually an IO operation. So let's explain how we can move a process from running to ready. Okay. So this, for example, happens when if you have a program that is running, a process that's running, and an interrupt occurs, for example, something that is quite important, like battery low or stuff like that, then the program, the process might just be moved from running to ready, so that the interruption handler function can be executed. Okay, so this is a possible way of when this happens. So when the process is executing and an interrupt occurs. From ready to running is instead it's basically the operating system that decides this. So the operating system have a queue of processes that are inside in the state of ready, and there is some sort of logic that runs inside the operating system that selects which process to run. So if the operating system, but specifically the scheduler, select the process to execute, then the process will move from ready to execute. So when the process is capable of using the processor and the operating system scheduler schedule the process for execution. Okay? And how to move from running to blocked. And this is basically, as I said, when an operation, if the code that is currently executing requires, like for example, that a keyboard press is entered, in this case, the program, there's no way that the process can continue until the user actually inserts a key, press a key on the keyboard. So in that case, the process moves from running to blocked, so that another process can run in the meantime while we wait for the user, for example. So when the process is executing and it needs to perform an IO. Okay, is this the end? No, we have other two questions, sorry. So the next question is explain why a process cannot be moved from the blocked state to the running state. Yeah, so that's something I kind of already said. Until the instruction, the IO operation is not completed, there's no way that the process can continue, because all the code that need to run will require that particular IO operation is completed. So there's no way that the process can run. So because the process needs put in ready state first after the IO operation is completed, so that the operating system can decide which process is best to run next. Yeah, so obviously cannot move the process cannot be moved directly from the block state to the running state. The first reason, of course, is that if the IO operation is not completed, there's no way that the process can run. So of course it's going to be stay in blocked state until the IO operation is completed. But even if the operation complete, it's not going to be moved directly into the running state. It's going to be moved to the ready state, because we want to make sure that the scheduler always run the process with the highest priority. So even if a process is ready to run and is not blocked anymore, we don't want to run it immediately. Okay, that makes sense. And the operating system's scheduler decide the priority based on the type of operating system or particular conditions, based on which processes are running, for example. These are particular algorithms that select which process is best to run. And the last question is explain the role of the high-level scheduler in multi-programming operating systems. So what I described before, the process of selecting a process from the ready state, from the ready queue, and move it into a running state, is basically what a low-level scheduler does. What a high-level scheduler does instead is decide which processes are to be loaded from the backing store into memory. Okay, so that's what the high-level scheduler does. The high-level scheduler decides which processes are loaded from the backing store into memory. Okay, so this is basically the end of the paper. As usual, if you have any question at all about the paper, feel free to reach out to angela.andrea@gmail.com or write in the Slack channel. So I'm more than happy to help you if there's something not clear about the paper. Thank you very much for watching.